Scientific visualization is the process of taking collected data and formatting that data in a way that is easier to comprehend. Traditionally, this data lives in the field while the visualization process takes place on a laboratory computer elsewhere. Our project utilizes a Microsoft HoloLens and strain sensors to bridge that gap. From left to right, Nathan DeStefano is in charge of visualization, Jason Stallkamp is in charge of data parsing, Justin Eckert is in charge of HoloLens integration, and Sam Ulrich is in charge of data generation. America's infrastructure is aging, and with age, the structures can potentially become unsafe due to shifting environments or updated building standards. In order to remove this potential threat, the structures must be assessed, which is a long and costly process. The assessment is complicated by the fact that these structures live in a dynamic world with shifting weather patterns, earthquakes, and general wearing. The purpose of structural visualization with augmented reality, or SVAR, is to aid in the analysis of infrastructure by providing a temporal and spatial context to data. It plans to do so by taking in sensor data, producing real-time scientific visualization that overlaps with physical objects. In the short term, the goal of this project is to aid in the testing and design of civil engineering experiments. The long-term goal of this project is to analyze the world's aging infrastructure by providing real-time data to those out in the field.
Now let's talk about the implementation. As far as four main parts. The first part is the data collection, which is handled by Daisy Labs, or in the case of Expo, a mock data source. The second is a parser, which handles the parsing and interpreting of data. The third part of the system is a visualization system, which renders the parsed data in a meaningful way. Finally, we have the HoloLens, which is in charge of displaying the data with AR.
Due to not having access to the structural engineering lab and active demonstrations of the sensors, we developed hardware prototype using an Arduino Uno and several potentiometers. This setup is used to simulate data collection. The Arduino allows us to output 5 volts through a 10 kiloohm rotary potentiometer and read the data back into the Arduino serial ports. The Arduino microcontroller board has a circuit inside called an analog to digital converter that reads the changing voltage and converts it into a number between 0 and 1024. As you can see in the code, we read from the ports and convert the 1024 range to a 0 to 5 volts to match the data output of the strain gauges used in the lab.
So now onto the parser. To understand the parser, we need to understand the data source. The data that we're going to display comes from the software Daisy Labs. This is a software that collects data from multiple sources and transforms it from a voltage level to a defined unit in a meaningful way. Luckily for us, Daisy Lab offers some hooks to export data to remote sources. The one that we use is a TCP hook, from which values are sent over the network to SVAR. SVAR receives this data as ASCII with a format of semicolon separated value. The string is parsed into raw floats with no mapping or units. This is because all we get is raw numbers. But the context of the data is important. We need data like the units, the position, and the name, so we add it back in. We do this by including an XML configuration file which is natively serialized and deserialized by C#. The final idea needed to understand the parsing is its concurrency. It is vital that the rendering happens as close to every 60th of a second as possible to reduce motion sickness. Now parsing and network operations can take a lot longer than 1/60th of a second. In order to maintain its frame rate, the parsing was moved onto a separate thread. Because SVAR also must work with Daisy Labs, which is a separate process, potentially on a different machine, Daisy Labs must be treated as a separate thread. It handles the passing of data between threads through a frame buffer-like data structure.
Microsoft HoloLens is a virtual reality headset with transparent lenses that allow for an augmented reality experience. According to Microsoft, HoloLens is a fully untethered, see-through holographic computer. This project utilizes a Microsoft HoloLens to allow researchers to look at structural component currently being tested and see live results at that moment. Ultimately, researchers will be able to walk around and view tests from multiple perspectives. To generate realistic, rapidly changing, three-dimensional holographic images in the user's field of view requires a lot of processing power, and those requirements each place 3 different kinds of demand on the processing system. To handle the load, HoloLens has 3 different processors: a central processing unit, or CPU, a graphics processing unit, or GPU, and a holographic processing unit, or HPU. In addition to this, there is an inertial measurement unit, or IMU. The IMU includes an accelerometer and a gyroscope. These sensors, along with head tracking cameras, track where your head is and how it's moving. The HoloLens uses its IMU to track the movements of the user and the infrared laser and camera to map out its local environment. These two streams of data are combined so that virtual objects mesh accurately with the real-world environment.
Every frame, we must update the visualization for each sensor. To update the color, we calculate a percentage based off the sensor's min, max, and current value. We then lerp between two preset colors, and then the lerp value becomes the color of the visualization. Lerp is a built-in Unity function that interpolates between two values when given a percentage. We also update the size of the visualization every frame. This is very similar to updating the color, where we again calculate a percentage based off the current value. Instead of lerping, we can simply multiply our percentage by the scale of the object in order to update the size of the visualization. After the sensor data is parsed and fed into Unity, we instantiate each sensor as an object in 3D space. Our early demo used spheres to visualize each sensors individually. These spheres can change in size, color, or both. The math to do this is quite simple. Given a min and max value that the sensor could possibly have, we calculate a percentage. Based on that percentage, the sphere will resize or recolor itself as a way to show a change in the sensor's value. Each sensor is labeled with a preset sensor name and displays a live value above it. We also have the ability to grab, drop, and scale sensors after they are instantiated. That way we can place the virtual sensor to match the real-world sensor's location. We are currently working on adding heat maps and contour lines as a new method of visualization. After speaking with our client, it was clear that they wanted to interpolate data between sensors in order to visualize real-time changes in the structure while it's being stressed.
SFAR is nearly complete, aside from a few more functionality implementations and testing. We need to continue implementing more methods of visualization data, such as heat maps and contour lines. This will allow for visualization that interpolate data between sensors. SFAR also needs further testing with Daisy Labs interface implementation. The current setup already uses the software to generate fake data for the HoloLens, and the next step is to test it in a lab environment for real sensors. Similarly, the interface between Daisy Labs and SFAR still has some bugs that causes crashes. It is unknown if these bugs are due to problems with Daisy Labs or the interface that we provide. Future implementation of our visualization technology with structural sensors will allow engineers and inspectors to visualize structural integrity in near real time under actual load. Observing how structures react under strain after construction or after an event such as an earthquake will help identify issues prior to structural failure or degradation.